Welcome to Chapter 18, Two-Sample Problem. In this chapter, we're going to look at the two-sample problem where the samples are independent. We're going to look how we compare two population means and use the T procedures to do these comparisons. We'll be doing confidence intervals and tests of significance. So that will lead us to the two-sample T procedures. We'll show how you use technology and then the robustness of these T procedures. Now, the goal of inference about these two-sample means is to compare the responses of two treatments or to compare the characteristics of two populations. We'll have two separate samples for each treatment or each population. Now, the individuals from one sample have no influence upon which individuals are selected for the second sample. So this is very different than what we saw at the end of Chapter 17. So again, the individuals from one sample have no influence upon which individuals are selected for the second sample. Each sample is separate. The units are not matched, and the samples can be of differing sizes. So in this chapter, we are going to look at comparing the average or the most typical responses or the typical responses in two populations. We're going to test claims regarding the difference of the two population means from independent samples. So two samples are independent if one sample has no influence on another. So, as I said in Chapter 17, we looked at the matched pairs, and that would violate independence since the one sample directly affects the other sample. We're going to construct and interpret confidence intervals regarding the difference of two population means. So let's turn our books, or you guys could go to your e-books, for looking at example 18.1. If you have your book, it's on page 472. And we're going to look at some examples of two-sample problems. Does regular physical therapy help lower back pain? A randomized experiment assigned patients with lower back pain to two groups. 142 of them received an examination and advice from a physical therapist. Another 144 received regular physical therapy for up to 5 weeks. After a year, the change in their level of disability from 0 to 100% was assessed by a doctor who did not know which treatment the patient had received. So this is an example of a two-sample problem. The one sample did not affect who was going to be in the second sample. Example number 2, a psychologist develops a test that measures social insight. So he compares the social insight of female college students with that of male college students by giving a test to a sample of the female students and a separate sample to the male students. Again, the female and the male, there's no one sample does not affect the other. Now let's look at the third example. A bank wants to know which of the two incentive plans will most increase the use of its credit card. So it offers each incentive to a random sample of credit card customers and compares the amount charged during the following 6 months. So these three are examples of two-sample problems that are independent. So to have for comparing the conditions for comparing two means, we have two independent simple random samples from two distinct populations. That is, one sample has no influence on the other, so matching violates that independence, as we've said before. We measure the same variable for both samples. Now, both populations are normally distributed, and the standard deviation of the populations are unknown. And in practice, it's enough that the distributions have similar shapes and that the data have no strong outliers. Now, in order to perform the inference on the differences of the two means, we'll need the standard deviation of the observed differences. So we're looking at the sampling distribution of the sample means for the differences of two means. And this is what the standard error would look like. And if you really look at this very carefully, you can see that this is really not very much different than the standard error for a one-sample problem. And let me show you what I mean by that. Now take a look at the bottom right corner. We know that the standard error for a one-sample problem back in Chapter 11 was sigma over the square root of n. But that really is, if we look at what sigma over the square root of n, it could come from the square root of sigma squared divided by n. Because as we know in math, with the square root, we take the square root of the numerator and the square root of the denominator, and that would equal sigma over the square root of n. So really, this standard error that we see up here is no more than what we're used to. It's just that because we have two samples, we can't separate these two and just say that that's the square root of sigma 1 over the square root of n1 plus the sigma 2 over the square root of n. That would be illegal math. So we have to keep it under the radical. Otherwise, really, that is just the standard error that we're used to. It just looks a little different because of the two-sample problem. So very clearly we can see that the progression of the square root of sigma squared over n is, you can take the square root of the numerator divided by the square root of the denominator, and you end up with what we're used to looking at as the standard error. So how that really is truly the same thing. But in this problem, we don't know the population standard deviation, so we're going to have to do an estimation. We're going to have to estimate sigma 1 and sigma 2 with the sample standard deviation for each of those samples. So now our standard error is going to look like the square root of s1 squared over n1 plus s2 squared over n2. That will be our standard error, and that will bring us to using table C, which is the t-distribution. Well, here we're going to see where how we find the degrees of freedom. We're going to use what's called the conservative method. And the conservative method is we're going to take the smaller of the sample. You look at the two sample sizes, take the smaller of the sample sizes and subtract it from 1. And that would be our degrees of freedom. And so we could now say how we would make a confidence interval for the difference of two means. We now have our statistic. It's x1 bar minus x2 bar. That's our statistic, is the difference of those means. So there's our statistic plus or minus our critical value, which is t alpha over 2. But remember, we also have to know the degrees of freedom, but we just figured out how to do that, times the standard error. So that's how we make our confidence interval. And these are the assumptions that need to be met in order to make a confidence interval using the technique that we just looked at. Both samples are obtained using simple random samples. The samples are independent. Neither sample has an outlier, and both populations are normally distributed, or both sample sizes are large. That is, n1 and n2 are at least 30. These are the usual conditions we need to make our student t-distribution calculations.